Hello everyone, you are watching Spider Bytes, where we make networking simple. In today's video, we are going to explore an important networking concept, packet forwarding. Have you ever wondered what actually happens when you send a message or an email? It travels across multiple networks, but how does it know where to go and how to reach the correct destination? It might seem like magic, but there is a well-defined process working behind the scenes. In this video, we will break down the journey of a packet step by step in a simple and easy to understand way. But before we dive in, having a basic understanding of networking concepts like IP addresses and data packets will be helpful. But even if you are new, don't worry. I will explain everything in a way that's easy to follow. Alright, to understand this journey, let's first look at our network. We have two different networks here. On the left side, we have a network 192.168.1.0/24, and in this particular network we have a PCA with an IP address of 192.168.1.1 and with MAC address of 1111. Now, in real networks, MAC addresses are 48-bit long values, but to keep things simple, we are using only 4-digit values like 1111. Similarly, there is a PCB with an IP address of 192.168.1.2 and MAC address of 2222. And both of these devices are connected to switch 1, and switch 1 is connected to router R1 at Z03 interface. This interface of the router has an IP address of 192.168.1.254, which is a default gateway of this particular network, and this interface also has a MAC address of AAAA. So, just like devices, every router interface also has its own MAC addresses. Now, on the right side, we have a network 192.168.2.0, and in this particular network, we have PCD with an IP address of 192.168.2.1 and with MAC address of 4444. Similarly, we have a PCC here with an IP address of 192.168.2.2 and with an MAC address of 3333. Both of these hosts are connected with switch 2, and this switch is connected with router R1 at the G04 interface. This particular interface has an IP address of 192.168.2.254, which is a default gateway for this particular network. G04 interface also has a unique MAC address of BBBB. So, this router is acting as a bridge between these two networks. Now, when data moves across this network, three important tables help in making decisions. First, the ARP table. This maps IP addresses to MAC addresses because devices need MAC addresses to communicate locally. Second, the MAC address table inside the switch. This tells the switch which MAC addresses is connected to which port. And third, the routing table inside router. This helps router decides which path to take based on destination IP address. Now, don't worry if this feels like a lot. We are going to see everything step by step. So let's take a simple example. We will send the data from PCA in a network 1 to PCD in a network 2. So as the packet moves, we will see how this ARP table, MAC addresses table, and routing table work together behind the scenes. Alright, so we are sending data from PCA to PCD. Now, the first thing that happens is something very crucial, the destination check. So PCA looks at the destination IP address and asks a simple question. Is this destination in my network or outside? PCA then compares its own network 192.168.1.0 with the destination network 192.168.2.0. Since these are two different networks, PCA realizes that it cannot send data directly. So instead of sending it directly to PCD, it decides to send it to its default gateway, which is router, with the IP of 192.168.1.254, which is a default gateway of this particular network. Now, before anything is sent, PCA creates a layer 3 packet, and this particular packet contains two very important pieces of information. The source IP 192.168.1.1, which is of PCA, and the destination IP 192.168.2.1, which is PCD's IP. And this destination IP is what will guide packet through the network. Since the destination is in another network, the packet needs help from the router. And routers make decisions using something called routing table. This table tells the router where each network is located. For example, 192.168.1.0 network is connected at the G03 interface, whereas 192.168.2.0 network is connected at G04 interface of the router. So, when the packet reaches the router will look at the destination IP, which is 192.168.2.1, and match it with the correct network 192.168.2.0, which is connected at the router's G04 interface. Now, you might be wondering how this information is in the routing table. Well, routers always make entries of their directly connected networks in the routing table. But before the packet even reaches the router, PCA still needs one important piece of information, which is the MAC address of its default gateway, which is the router's interface connected to the network 192.168.1.0. And that's where ARP comes into play. ARP stands for Address Resolution Protocol. What is ARP? It maps the logical IP address to MAC address. So in simple terms, it helps a device to find the MAC address of another device when it only knows its IP address. Because remember, inside a local network, devices don't usually send data using IP addresses. They use MAC addresses for delivery. So even though PCA knows the IP address of the router, it has no idea what the router's MAC address is. So how does it find that MAC address? Well, by using ARP request, which is broadcast message, and ARP reply, which is a unicast message. Now, let's look at how this actually works in detail, starting with the ARP request sent by PCA, which contains a few important fields: source IP address, destination IP address, source MAC address, and destination MAC address. The source IP 192.168.1.1 is PCA's IP address, and the destination IP 192.168.1.254 is the default gateway of the local network 192.168.1.0. The source MAC address 1111, which is PCA's MAC address, but notice the destination MAC address here. It is set to FFFF, which represents a broadcast MAC address. It means it sends this message to every device in the network, because at this point PCA doesn't know who has that IP address. Now, let's see what happens when this ARP request reaches the switch. As soon as switch receives the frame, it looks at the source MAC address 1111 and it learns that this MAC address is connected to the specific port G00, and this entry is going to be stored into the MAC address table like this. This process is called MAC learning. Now, since this is a broadcast frame, the switch forwards it to all connected ports except the one it was received on, and each device going to check the destination IP address inside the request, and if the IP does not match, the device simply discard the request. For example, a broadcast message received on PCB will be discarded because destination IP 192.168.1.254 is not going to match with PCB's IP 192.168.1.2. So, only the device with matching IP, which is the router in this case, will respond. So now the router recognizes its IP and sends back an ARP reply. Now, let's look at the ARP reply sent by the router in detail. Just like the request, the ARP reply also contains crucial fields, but now the source IP is the router and the destination IP is PCA. The source MAC is the router's MAC address, but notice the destination MAC. This time, the destination MAC is not broadcast. It is a PCA's MAC address 1111, which means this is a unicast message. So instead of sending to everyone, the reply is sent directly to PCA. Moving forward, switch 1 also checks the destination MAC address in ARP reply, and then it looks up this address in its MAC address table and finds the correct port, which is G00. The switch then forwards the frame out of that port. As a result, PCA receives the ARP reply and stores the information in its ARP table. So now PCA knows the MAC address of its default gateway. And now it finally has everything it needs to send the actual data. So let's see how the frame is created and forwarded. First, PCA starts by creating a frame, which is like a package used to send data on the network. This frame contains both layer 2 and layer 3 information. Layer 2 part includes MAC addresses, while the layer 3 part includes IP addresses. PCA sets its own MAC address as the source and the router's MAC addresses as the destination. However, notice the destination IP address. It is still PCD's IP address. This is because IP identifies the final destination, while MAC addresses are used only to reach the next hop. So, original layer 3 IP packet remains unchanged. Now, this frame is sent to the switch. The switch receives the frame and checks the destination MAC address into its MAC address table and finds the correct port connected to the router, which is G01 in this case. So instead of sending it everywhere, it forwards the frame only out of that port to the router, which is G01. Once the frame reaches the router, it removes the layer 2 information and looks at the layer 3 IP packet inside. It then checks the destination IP address, which is 192.168.2.1, and refers to its routing table. The router finds that this destination belongs to the network 192.168.2.0, and based on that, it determines the correct outgoing interface As a result, router forwards the packet out of G04 interface. But before sending it to the next network, router needs one more thing. It needs the MAC address of the destination device PCD. And just like PCA used ARP earlier, the router will also use ARP in this network. So router sends an ARP request in the network 192.168.2.0. The message looks like this. The source IP and MAC address of the router, which are 192.168.2.254 and BBB respectively. The destination MAC is again set to FFFF, which means this is a broadcast message because router still does not know the MAC address of PCD yet. Now, this ARP request reaches to this switch, which looks at the source MAC address, which is BBBB, and learns that the router is connected to this port G00. So, now this entry is added to the MAC address table of the switch. Since this is a broadcast frame, the switch forwards this ARP request to all the connected devices. Now, every device will receive the ARP request, but each one checks the destination IP address, which is 192.168.2.1, and if it doesn't match, the request is discarded. Only PCD recognizes its IP 192.168.2.1. So now PCD sends the ARP reply back to the router. This reply contains PCD's MAC address. Notice, this is not a broadcast, it is a unicast message sent directly to the router. As the switch receives the frame from PCD, it learns the MAC address of PCD, which is 4444. It belongs to the PCDs on the port G01. Now, the switch knows exactly where PCD is located because this entry is saved in its MAC address table. Moving forward, switch also checks the destination MAC address, which is BBBB. It looks up this address into the MAC address table and find its outgoing interface, which is G00, and sends the ARP reply to the router. First, router checks its routing table to see if it knows how to reach the destination network. Since it already has an entry for the destination network 192.168.2.0, it forwards the packet out of G04 interface. Earlier, the router already learned PCD's MAC address through the ARP process, so its ARP table already contains the mapping for IP 192.168.2.1 to MAC address 4444. Because of this, router can immediately use that MAC address without sending another ARP request. Moving forward, the router encapsulates the packet into new Ethernet frame, which is layer 2, and the destination MAC address is set to 4444, while the destination IP address in layer 3 remains 192.168.2.1. As the frame reaches to switch, it checks its MAC address table, and since it already knows the MAC address 44444 is connected through the G01 interface, it forwards the frame directly out of this particular interface to PCD. Finally, PCD receives the frame, removes the layer 2 and layer 3 headers, and process the actual data at the application layer. So, that's what really happens behind the scenes when packet travels from one network to another. It's not magic, it's ARP, MAC tables, and routing tables working all together step by step. Once you understand this flow, networking starts to make a lot more sense. If this helped you understand the concept, make sure to like the video and subscribe for more CCNA tutorials. Thanks for watching. I'll see you in the next one.